Hello everyone, and welcome back to another tutorial. Sorry about the long wait. I'm not going to tell you where I was, but I'm sorry I missed you all. So today's lesson, I'm going to take on a wee bit of drawing with a frame buffer. So the idea is here, we're going to draw off-screen using another image, and then use that image to draw onto our final screen. And if you've done any kind of like rendering or engine stuff, you might know this as a back buffer or something else. But the basic concept is to take frame buffer, draw our scene onto that, then take that frame buffer and draw onto our final screen, effectively compositing it. It's a fairly straightforward concept, but it's one of those ones that will be very handy in ways that you won't even think about. Especially if you're doing things like multi-layers or sort of post-render effects onto the screen. So we're just going to go straight in here, and if you've followed along from the previous tutorials, using part 2 as the basis of making this next tutorial. So let's just go ahead and create a new class here, and we're going to call it back buffer. And to get our constructor going, we're going to take in our GL context, and then we're going to take in any options that we might want to specify at a later point. So store the GL context as part of the object so we can refer to it later. And then we're going to create a material associated with this back buffer. So new material and... But if you're following all of these once they're uploaded, you can see up here whenever we create a new material, it takes in the GL context, the the vertex shader as a string, and the fragment shader as a string. So we're just going to stick in this.gl, but for these I'm just going to leave them blank for the moment. We'll come back and fill those in later. We will need at least a custom vertex shader for this, but I'll show you that once we create the rest of the class. Okay, we're going to create a new size, which is going to be a point, and our default size would be something like let's say 512 by 512. That's big enough. Now, for a modern game, if you're doing if you've used Unity or anything like that, 512 is obviously tiny. Modern resolutions can go usually start at about 1,800 pixels tall and can go much higher than that. So obviously this is only really appropriate for low resolution games, but I assume that's alright for the moment. So okay, we'll go if width is in our options, and we want to set this.size.x to options.width. So there we go. That lets us to put in a few custom parameters. And we'll do the same for the Y direction. Okay, so let's create a few buffers. So we create a frame buffer itself. So we go gl.create frame buffer. Okay, then we also want to create a render buffer. So we'll call it r buffer equals gl create render buffer. And then lastly, we want to create a texture, which will be the actual, grid of pixels that we'll be rendering to, and that we can refer to later whenever we go to render it on other contexts. So we create texture, no, not texture, text node, texture. Okay, so that's our that's all those created. So let's start binding stuff. Bind frame buffer. Oh, quick correction here. These should be frame buffer with I did the camel case, but it's frame buffer lowercase b and render buffer lowercase b, create texture uppercase t. And that's the same for bind frame buffer. It's also a lowercase b, and gl frame buffer, all uppercase because it is a constant, and that is the typical way you denote a constant. Okay, so we just bound our frame buffer, and then we're also going to bind our render buffer. Only this time, since it's in frame buffer, it'll say, you guessed it, render buffer. No, not renderer buffer, sorry. GL, then bind texture. This is our new texture. The GL, what type is it? Is it texture 2D? and here is its reference. Okay, so let's set the parameters for our texture first. So GL text parameter, you might remember we did this before for the sprite, so this should be fairly familiar. And put in our type, texture 2D, and we can set texture our wrap S, and what parameter will we give it? We'll give it clamp to edge. Clamp to edge. And what clamp to edge does is once our reference hits outside of the image, it means that instead of mirroring or flipping or whatever, it'll just stretch out the sort of border pixels out forever. It's not really going to be relevant here, but I just thought I'd reiterate what it was. T and S. Okay, now let's do our texture filtering for if the image is larger than the original sample. We want to use nearest, so that'll be very pixelated looking, which will match the rest of our aesthetic for this game. And if the texture we're sampling is smaller than the original, we'll also use nearest. So yeah, it'll be very pixelated. If you've ever used Photoshop, you might be familiar with this concept. Okay, so text image 2D. Right, so we put in our type again. So what we're going to do here is we're actually going to tell our OpenGL layer what some parameters about the actual texture itself. So it's going to be a texture 2D, which we know. Some kind of 0 goes in there. There's like plenty of these things I'm not really that familiar with, and it's never come up, so I've never learnt them. You can look into the documentation if you're curious yourself about more details about what some of these parameters are, but I'm sure RGBA is pretty obvious. It means that we have a red, green, blue, and alpha component. For size, that's again quite straightforward, which is the X and Y size that we recorded earlier. That's the size of our texture. Another random 0. GLRGBA again, and we wanted to store as GL as an unsigned byte. Sorry. And what an unsigned byte is, for anybody not from a computer science background, is a byte which is 8 bits, and there's no sign for minus or positive, so the number goes from 0 to 256. Okay, and a random null. I have no idea what that null is for. Okay, with the parameters set for our texture, let's move on to the render buffer. So GL render all lowercase buffer uppercase storage, and GL uppercase render buffer. We used it earlier. GL. Some of the stuff is fairly routine. Necessary parts of defining the parameters of different things we create. So we're doing the sort of same thing again, same size as our texture. It's got a depth component which we probably won't use, but I may as well add it. And not exactly the most efficient to create something we're not going to use, but yeah, suit me. Okay. And now we're going to associate our texture that we created with our new frame buffer. So GL frame buffer this time. GL color. Oh, sorry, I keep spelling with U. Attachment 0. GL texture 2D. Oh, like that. The actual texture. This is our created texture, and then a random 0. Let's assume that's a slot or something. Frame buffer. Okay, so we're going to associate the render buffer with the frame buffer. So it's render with a capital R, but buffer with a lowercase b. GL frame buffer. GL depth attachment. GL render buffer. In this case, you can see there's room for multiple color attachments, but only one depth attachment, which makes sense. Our buffer. I won't go into any detail about like how depth testing works in 3D programming, mostly because it will not really come up in a 2D engine. And let's see. So, okay, let's create our actual geometry now that we've set up the parameters for our various buffers. So, just a little comment here. Should create geometry for rendering. Okay, let's get this. Ooh, no. Make it a bit bigger on the screen. Okay, so we create a new buffer. We'll call it our texture buffer, our TEX buff equals GL create buffer. I've created a few of these now, so let's set some parameters for it. First of all, we need to bind it. Bind buffer GL array buffer. That's what it is. And we put our object in, then our newly created object, and then we set a parameter for buffer data GL again instead of still an array buffer. Type. And we're going to use something we created last time for convenience, which is sprite create rect array and GL static draw, because it's going to be mostly the same. So what does this create rect array? If you're following again at home without any kind of break between these videos, you probably remember what this was. But all it does is it returns a box, effectively two triangles as a buffered array that starts at X and Y and has a width W and of height H. And what it does is just creates these two triangles as array data and then sends those back. So it's very convenient for creating very simple square geometry for rendering sprites, because it's going to be such a repeated task for so many different sprites. With just all that's going to change is the variety of sizes. It's very handy to have a function that does this for us, and we can even use it here. And if I leave the parameters blank, you can see that the automatic parameters are 0. It starts at 0, 0, and then it is a width of 1 and 1. So you know, 1 unit square effectively that starts at 0. That's exactly what we want for our UV coordinates. And then after our UV coordinates, let's do our world coordinates for our vertices. And we start by creating a new buffer. So this is going to be much the same as the top line. In fact, it's going to be so similar. I'm going to copy them. And so GeoBuffer goes in here. But this time, instead of create array where we leave all the values empty, it's going to start at -1, -1. And it's going to have a width of 2 and a height of 2. And that, if you're familiar with OpenGL, you'll realize that's the size of the default values of the screen. So that'll fill an entire screen in OpenGL, as the default coordinates for OpenGL is between -1 and 1. I know that's not very well explained, but it's very difficult to explain these sort of rudimentary concepts of OpenGL if you're not familiar with them already. So if you're not really sure what I'm talking about there, just take it as a given. Okay, and then we're just going to remove these things from our bindings. So render buffer, which we're going to bind to nothing, our texture 2D, which we bind to nothing, and finally our frame buffer, which we bind to nothing. I don't know if you have to do that, but I feel it's good practice. Alright, and hopefully there's no syntax errors. Yep, seems good. And if I can create a new back buffer here in the console, so bb equals back buffer, it should probably throw an error given there's no defined shader, so these are still blank. Right, so let's actually create some shaders for these. And the one thing I will say, now this is probably a bit hacky, we're going to create a constant string which will represent the vertex shader for all these back buffers. They'll all use the same vertex shader because it'll always have the same way of rendering. So what I'm going to just type in here is vertex shader. So just maybe VS like that. And I'm going to create a multi-line string, and you can do this by using, what do you call this character? If you've played video games, it is, and I'm assuming you have, given you're making a game engine, it is the console key, I think sometimes called the tilde key. It is above the tab key, on UK keyboards, and what it is like a little sort of sideways apostrophe. That'll let you type in multiple lines of text without like having normal syntax errors. So our vertex shader is going to be very similar to our pre-existing vertex shader. So I'm just going to copy that from our index.html into our back buffer like this. And I'm just going to fix the tabbing here. Okay, so a few things we won't need. We won't need any of these matrices and the U-frame. We'll be using the vertex shader to render just one large rectangle over the entire screen. And then we need to get rid of those here, so our matrices, we just delete those. And then I can probably simplify this a little bit. Instead of having a couple of different cascading, instead of having some nested vec3 into vec4, I'll just have one vec4. Okay, and then we get rid of this U-frame. Audio Rabbit. Sorry, I think I made that joke last time, I'm sorry. And I think that's it. So, well, it still causes an error because I haven't plugged it in. But it means that I can now plug in a vertex shader into here. And so that way we'll do the same thing with our fragment shader. Though in this particular case, I don't think we'll need to really modify it at all. So I'm just going to do back buffer fs, same situation. And we'll fix the tabbing again. So what have we got? Yes, it just samples an image using the vertex parameters created by our back buffer, created by our vertex shader, and that should be it. Okay. So once we put in our GL context, which is game.gl, hopefully, and an empty set of options, we get loads of errors, which is to be expected because, you know, there's still a lot more work to get done. But it's off to a rough start, but, well, you know, we'll work at the kinks later. Alright, well, let's get back to our main game loop. And today we're going to use a couple of new sprites for testing this whole business out. And let me see if I can find them. Yes, here they are here. So we got this halo sprite, which is a sort of black square that gets a progressively white halo towards the center. We're going to use that as a light source, and we're also going to use this white.ping, and it's a 1x1 pixel sprite of a white pixel. Just it's a very convenient thing to have in any project. I mean, you don't necessarily have to have it loaded in like this. You could generate it, for instance, but I think it's just as convenient to keep it as straightforward as possible for now. So we're just going to load in that 1x1 pixel thing. But the important thing to note here is halo, because that's the thing we're going to be using. And let's just load them in here the same way we did our other two sprites. So the first one is halo. Oh, butterfingers. Halo.gif. I don't know why it's a GIF, but I made it a GIF. White.png, and a width of 256 by 256. This is a width of 1, a height of 1. And let's give them proper names. Halo and white. Okay, so if I refresh this, everything's fine, and I'm just going to render that halo first, just to demonstrate that it has loaded in. So halo.render and white.render, although white's so small I'll probably not be able to see it. But yes, you can just see the white pixel in the corner, and obviously you can see the halo, it's huge. So that means, like, yeah, we've loaded in our new files successfully, but we're also now going to create our back buffer. So this dot, let's just call it light buffer equals new back buffer. This dot GL is one of the parameters, and for the moment I'm not going to put in any parameters just yet. And yes, of course, it's going to break things for us because we haven't finished writing our light buffer just yet. just to correct a mistake I made earlier, this shouldn't be bind frame button. It should be bind render buffer. Sorry, sometimes when I code these things from the flag and make a few mistakes here and there, and that of course has fixed things for us. So we're going to add in a function here as part of our main game object, and what it is going to be set context, or set, we're going to call it set buffer, and then we're going to put our buffer in. However, let GL equal this.gl for convenience. If buffer is an instance of back buffer, fine, that's great, we'll just go as usual. However, if it's not, what I'm going to do is I'm going to make it reset things. So if I send nothing in here as the buffer, I'm going to assume we're going to go switch back to our main context to render to and not one of the frame buffers to render to. So to do that, we just simply have to do GL. So get rid of the GL viewport, and then we set it to whatever the normal viewport is, and then we bind frame. I keep using the capital B. Buffer GL frame buffer, all uppercase, and then null. So if you don't provide a frame buffer, then use the frame buffer of null. And to get things kicked off, we're going to get this dot set buffer. We put in nothing, and there you go. Things are working again, because before it starts rendering everything, it sets the frame buffer to nothing. However, if there is a frame buffer, you want it to set the frame buffer, well, to that new buffer. So we'll go buffer f buffer, and f buffer is of course the frame buffer within the buffer. And if I say buffer anymore, I'm going to turn into a buffer. And if we do use the buffer, we want to clear it first. So we go gl.clearColor. Okay. And we also want to change the rendering area to buffer.size.x and buffer.size.y. So our rendering area will be the size of the texture that we actually created as part of our back buffer. Alright, so far so good. Right, now we need to write a rendering function to go along with our back buffer, so that way once we're done writing to it, we can then write it onto the main screen. And to do that, we'll add a render function, and this will be pretty straightforward, like all the rendering functions we written in the last tutorials. So gl equals this dot for convenience, this dot gl use program, and it's going to be our shader, this dot material program. Sorry, say shader, what I obviously mean is material. And then we want to set up our texture, so we active texture, and we want to set the active texture to GL texture 0, texture in this first slot. GL bind texture. Okay, it's going to set our current texture to use the texture associated with this back buffer. And then this dot material set u image to 0. Alright, now we have a texture. We need to do the same thing for texture coordinates. So again, we bind the buffer, and it's a type array buffer, bugger, no. This dot text buff. Okay, so what now we've got this set up, we just need to go this dot material a dot texture coordinates, and this will use whatever texture coordinates are currently in the buffer, and we put in the texture coordinates up here at the start when we first declared it, so we'll have the right coordinates already waiting for us. We just need simply to tell the rendering engine that's what we're using. So bind buffer, and it's the same thing. In fact, copy and paste. We're going to do this for the geometry, and instead of a, it's going to be a position, instead of our texture buffer, it's going to be our geo buffer. And then we simply draw the lines. GL, draw array. GL, and it's a triangle strip. Starts at 0, and it is 6 vertices long. And then we set the use program to nothing, just cleaning up afterwards. And that's our rendering function. Okay. Now, fingers crossed, I don't expect this will work right away, but what I'm going to try here is, so I've created my back buffer. If we go back to our game page, we see we've created our back buffer, our light buffer. So rather than render the sprites on these sprites here onto the main screen, I'm going to render instead use this set buffer, and we're going to use our new light buffer. And then when we're done with that, we're going to set it back to the main buffer. And then hopefully we can just do this dot light buffer render. And while it has seemed to have worked, we are rendering our halo and our white dot onto our back buffer. The back buffer seems to be including our first couple of sprites. So maybe if I just change the sprite order and render these afterwards, that'll restore them. There we go. So we are rendering our stuff onto our back buffer, although it's hard to tell that that's actually happening because it seems to be the same result. So just to kind of mess around and show that like what a back buffer is doing, I'm going to set its resolution to something ridiculously low, and you'll see how that might affect it. Width 32 and height 32 as well. And there you go. Now I think that makes it pretty clear what's happening. So we're rendering our sprites onto a super low resolution back buffer, and then that's being rendered onto the main screen. And the result is that we have a highly pixelated element being rendered onto our main screen. So there you go. You can see the concept works. Well, what's the point of this? I hear some facetious person say in the comments, and to that person I say, shut up. Well, what we're going to do now is we're going to change the way these the back buffer layers on top of our work. So I'm going to move these back so they render before our back buffer renders. So there we go. So they'll be included by our back buffer again. However, this time, before we render our light buffer onto the final screen, I'm going to change how it blends. So instead of using our alpha to blend it, I'm going to just make it simply add onto the screen. And there you go. You can see that like one layer is laying on top of the other and affecting it. That's a simple additive effect, but maybe it would be better if it was more of a multiplicative effect. So we put in, instead of 1, it's destination color, and instead of 1 here, it's 0. So there we go. This is our back buffer is now rendering in a cornflower blue, and then it renders the halo. But then that information is then rendered on top of our screen using a multiplication blend method, and that overall lowers the color of our final render. So where we're rendering this white square here, I want to do something else. Now I'm going to put in some options here, and this won't do anything for the moment, but you'll see what I'm getting at in a minute. So if I type in scale X and make it scale, instead of 1 pixel, I want to make it, let's say we make it 240, and so it's going to scale it up by 240 times, and I'm going to do the same for the y-axis. That shouldn't do anything yet because I haven't set it up. But if we go back to material and we look at our sprite rendering, we see we take in the parameter of position and the frame we want. Now I'm going to put in a new one called options. And so below use program, I'm going to create a for loop. I'm going to go for option in options. So it'll cycle through these. If anything exists in here, it'll cycle through all the options in the options. I'll want these to apply to our shader. This dot material dot set dot apply context. This material again, and we need to put in the name so of the parameter, so it'll be option, but then we also want to follow it up with concat. And if you've worked with JavaScript a lot, you'll know what I'm doing here. It looks a wee bit messy, but it's quite a compact way of simply taking our list of parameters, so options, and then our option, and turning those into arguments that we can then use in our materials set function. So the name, and then parameter A, B, C, D, E, and what we do is there's the name option that we get out of it, and then our options, or you know, the array of information that we'll then concat into a big list of our big array, which will then become the parameters of our function. If you don't know what's going on there, that's all right. It's kind of a bit of a sort of messy way, or not messy, but a very compact way of doing a very simple function call. So if I run that again, it shouldn't affect anything. The shader doesn't have any property called width. So instead, we're going to do if scale x, or if our option is called scale x, I want to handle it specifically by affecting our transformation matrix for the object, and we do that by simply going this that equals scale, and if it's going by the x-axis, I want to scale it by options scale x like this, and we don't want to affect our y-axis. However, we do want to affect our y-axis if it's scale y, whereas we don't necessarily want to affect our x-axis. So we just need to change this to scale x and scale y. And so it goes through the options we provided, but if one of them is called scale x, it changes our matrix to scale along the x-axis, and if it's called scale y, it'll scale our matrix across the y-axis, and this matrix here is the object matrix. So we run that, and there you go. You can see now that this 1 by 1 pixel sprite has now been stretched to 240 by 240, which fills the screen. And so now we've got this nice little rectangle here. Right, so in addition, however, to having our options like this, I'm also going to have some default options get applied to. And for example, I want to this material set, and I'm going to call it uColor, and the values of uColor will be 11111. And so unless it's changed by our custom options, the material's uColor value will always be set to 1111, which is white, and you see it doesn't have an effect because there's currently no parameter called uColor in the shader yet. But I can go to my fragment shader, create a new uniform called uColor of type vec4, and I want to multiply our final color with that value. And that doesn't have any effect yet because we've set it to white, but I can assure you if you go in and change one of these values to 0 and 0 and run it, everything turns a horrible blood red shade. So what's happening here is our uColor value is being set to 1001, which is full red intensity, no green, no blue. And in our shader, we then use that uniform to multiply our final colors together, effectively reducing those channels to 0. But for now, default 1, 1. Okay, so the reason why I'm doing this is that way if I go in, save that. If I go into game, and here where we have scale x and scale y equals 240 and 240, if I also then set uColor to red, so same color, 0, 1, 1, 0, like this. Oop, don't forget your comma. That'll change that square to be a 1 by 1 red thing that's stretched out to fill the entire screen and turn it all a horrible blood red. However, if I render this first and then the halo afterwards, what'll happen is we'll render the red square, and then we'll render our halo on top of it. However, if I render the background first over top of everything, and then render my halo using 1 here and 1 for the destination color. This is again setting my blend function to additive. It'll add the whiteness of this halo on top of the redness of the background, creating a sort of like a white circle in the center of the red, and then that'll make a kind of red sort of spotlight. So let's just get rid of, for start, let's stop moving, create the sort of look we want. It's 512, so it'll, across the x-axis. Make this 512, and I'll stop it from moving by just saying new point. Okay, and same for this, new point. And again for halo, I don't need it to do this, so new point. And that should stop it from moving, staying the same, but the spotlight of the halo will move across. And now it looks like we've got something of a spotlight, especially if I start making the colors look dark. So if instead of this, it's make it 0.125, 0.125, and 0.25. Now it looks like the screen's dark and it's being lit by this kind of lighter circle here. And I'll just increase the resolution there so it doesn't just look so bad. So 240 by 512. And there you go. That looks like a nice little piece of light moving across the screen, lighting up the objects behind it. Just maybe I'll stop it from moving so you can sort of see how it interacts with some objects behind it. So where I've got it here, I have view point, and I'll set it to 32 by minus 64. Look. And there you go, you can see as the object behind it kind of lights up as it moves in front of it. Now this is nearly done. I think this concept's fairly well rung here, but I think one thing that's probably going to be good practice moving forward is we're using this light buffer here to kind of draw our lights onto, but we should probably use a buffer for drawing all our background onto and then drawing it onto the main screen at the end. So in addition to this light buffer, I'm also going to create something called a back buffer. The back buffer is going to operate much the same way as our light buffer, except we're going to render our sprites to it. So whenever we get to this point here, I'm going to set this set buffer to this back buffer, render our sprites to it, and then I'm going to set the light buffer, draw our lights onto it, and then finally we go to draw onto the actual screen. And first of all, that back buffer dot render, and we want that to use the regular alpha channel to render, and then we wanted to render the light afterwards using a multiplication blend method. And there we go. It doesn't really look like a whole lot has changed. However, we are now rendering things at a lower resolution. So for instance, if I was then to go into my back buffer and say for whatever reason you wanted to run the game at like a Game Boy's resolution of like 102, you can create much more pixelated graphics without having to like resample your original images. And it doesn't hide things like kind of fake looking subpixels that wouldn't really happen on low resolution displays. But overall, that's the concept of rendering off screen. And now that we've set it up, we can set up as many arbitrary back buffers as we want. And what we can do is we can create 2 back buffers, which we render to one while sampling the other, and then flipping them over and doing the same in reverse. And like you can do this kind of whole like multi-sampling between like several buffers kind of effect. So you could draw like a sprite in the background and see what's in that background and draw on top of it and that kind of stuff. So this is a sort of good, important step, I think, to like a modern engine. You don't necessarily want to be just drawing stuff directly onto the onto the screen. You kind of want to draw it off screen and then manipulate whatever that is afterwards using post rendering effects. But that'll do for now. I keep it again quite short, but I think this is a very useful one. I hope that it's been clear enough. It's one of those concepts that I say will be very useful, and you'll find lots of neat ways of exploiting it later as you get more confident with like the kind of things you can do with like a post rendering effect. Anyway, thanks for watching, and I'll see you next time. Thanks very much.